This is a video about how to solve electric fields problems. So in this particular problem, we've got a proton that's right there, and it's a distance of 3.8 times 10 to the minus 15 meters from location X, and there's also an electron right there, and it's a distance of 6.7 times 10 to the minus 15 meters from location X. And we want to find the magnitude of the electric field due to the proton. So the proton first, we want to know what the value of the electric field is that it produces at location X. So this is the equation we use for the electric field from a point charge. So because this proton is behaving like a point charge and it's creating an electric field, that means it's warping the space around it, we're going to use this equation to find the electric field. So we use K, which is our constant, 9 times 10 to the 9th, the charge of the proton, and the distance d1 that the proton is away from location X. And we get a value of 9.97 times 10 to the 19th newtons per coulomb. And it's important to say what direction that is. So remember what we have to do is we have to assume that at location X, there is a positive test charge there. A positive test charge. Since the proton is also positive, it's going to make the test charge repel away from it. So that's why it's going in that direction, upward. Okay, so now let's look at the electric field due to the electron at location X. So same thing, we're going to use the same equation for a point charge. This time we're going to use the charge of an electron. It happens to be the same. Notice we're leaving the negative sign out of this problem because we're more concerned about the direction as it's laid out for us on the picture as opposed to whether or not it's positive or negative on a line, for example. So the distance d2 that the electron is from location X is 6.7 times 10 to the minus 15th meters, and we're going to square that. And we get a value of 3.21 times 10 to the minus 19th newtons per coulomb. Now, at location X, once again, we assume that there's a positive test charge there. The electron will attract it and produce an electric field pointing towards the electron because, again, it's attracting it. It's attracting this imaginary positive test charge at location X. All right, now we want to find the net electric field. So we've got our two electric fields, this electric field and that electric field there. But the issue is that they're not head to tail. So we've got to move them. So let's move this one first. Let's move that up to where you can see it up there. And then let's move the other electric field vector so that now they're head to tail. Okay, so that's this hypotenuse is what we are actually looking for. This hypotenuse, that's our net electric field. So because that's the hypotenuse of a right triangle, we can use a Pythagorean theorem and solve for the net electric field there, and we get 1.05 times 10 to the 20 newtons per coulomb. So that is our new electric field strength. That's a net electric field. So now we want to find the angle that this net electric field produces at location X. So there's our angle. And again, we're going to consider clockwise to be positive. So we use the inverse tangent of the opposite side divided by the adjacent side to find that angle. And it turns out to be 72.2%. I'm sorry, 72.2 degrees. So the full answer of what is a net electric field is that it is 1.05 times 10 to the 20 newtons per coulomb at 72.2 degrees above the positive x-axis. The next question asks us to find the net force. So we've got this value for the electric field. that a proton placed at location X would experience. So here's what we're going to do. We're going to put that proton right there at location X, which essentially means we're putting it right there. Okay? And we want to know what net force that proton experiences. So we use the definition of the electric field, the fact that the electric field is the force per unit charge. So it's the force that it experiences. That's what we're solving for, that net force. The electric field, which we know its value, that's what we solved earlier. That's a net electric field. And we're going to use the charge in question, the charge that we're accelerating, the charge that's experiencing that electric field. And that is the charge of this mu proton that we'll call P2. So we rewrite the equation for the force, and we take the electric field and multiply it by the charge of the new proton. So that was 1.05 times 10 to the 20th newtons per coulomb. The charge of a proton is 1.6 times 10 to the minus 19 coulombs. So we get a value of 16.8 newtons. Okay, so that's the value of the net force. So the angle of the net force, notice that our net force vector points in the same direction as our electric field vector. So what that means is that our angle is the same angle we had before, 72.2 degrees. All right, now we want to find the acceleration of this proton at location X. So we know that Newton's second law says the sum of the forces equals the mass times acceleration. In this case, our force, we've only got this one force of 16.8 newtons. We divide it by the mass of the object we're accelerating, which is our proton, the mass of the proton. Remember, we get this value of the mass of the proton from your table of information. So the force divided by that mass gives us an acceleration of 1.00 times 10 to the 28th meters per second squared. Our next question is, what is the angle of that acceleration? Well, the angle of that acceleration is the same as the angle of the force. Newton's second law says the direction of the acceleration has to be in the same direction as the net force. So in this case, they're both 72.2 degrees. Okay, now this question says, assuming the proton at location X starts from rest, and that acceleration is constant, which it probably wouldn't be. This is just sort of a question that I made up. It says, how fast will it be moving after 1 times 10 to the minus 22 seconds? So let's look at what we know and what we don't know. So first, we know starting from rest, so the initial velocity is 0. We also know that the acceleration we saw before was 1 times 10 to the 28th meters per second squared. We also know that the time is 1 times 10 to the minus 22 seconds, and we are looking for how fast it's going. So those are the four variables. The four variables that we know we don't know. There's a 3 that we know. There's a 1 we're looking for. The only kinematic equation that would work is that equation there, v equals v initial plus at. And so we're looking for the final velocity. So we plug in our values of 0 meters per second for v initial, for acceleration, 1.00 times 10 to the 28th meters per second squared, and 1 times 10 to the minus 22nd seconds. And we get an answer that looks like it's 1 million meters per second.